The following question is about uniform circular motion. We have a roller coaster that's 100 kilograms, moving at 15 meters per second in a 5-meter radius circle. We want to find the normal force that pushes on us at the top, also the minimum required velocity to keep us going within the circle. Now, first thing is remember is that in uniform circular motion, we have centripetal acceleration, making sure the cart is going in this circle. Now, if we represent this centripetal acceleration as a force, we would have to multiply it by the mass of the cart. Now, this is representative of a force going inwards. Now that we have that, we can actually draw a free body diagram of the forces working on this cart. So, what forces do we have? Well, we have the normal force experienced by the surface, or the cart by the surface. And then another thing we have is the weight, which is also mass times gravity. Now, if you look, the normal force is in the direction of centripetal acceleration, and then the weight is not. So if we represent the centripetal acceleration at the bottom, we have normal force minus gravity, or minus the weight. Now, if we did the other way around, where we're at the top and centripetal acceleration is downwards, we have the normal force, which is pointing this way, because the surface is pushing down. And then we also have gravity times the mass, which is the weight, also going down, because that's where the direction always is. So if we represented that, we have mass times centripetal acceleration to represent it as a force is actually just equal to the normal force plus the weight. So if we have the centripetal acceleration at the top, and then we have gravity and times the mass, which is the weight, and we have the normal force, we can actually solve for this normal force. But in order to solve for it, we first have to know what centripetal acceleration is. Well, centripetal acceleration is calculated by v squared over r. So over here, if we just subtract by the weight on one side, we can solve for the normal force. So we get mass, which is 100 kilograms, times centripetal acceleration, which is 15, which is the velocity, squared over the radius, 5, minus the weight, which is 100 kilograms, times gravity, 9.8. We just actually get 3,520 newtons. So that's the normal force that you experience at the top of the loop. Now, what minimum velocity is required to keep us going in this loop? Now, I'm going to say that in the top of the loop, our minimum velocity is experienced when our normal force is 0. And let me tell you why. So let's rewrite this. We have centripetal acceleration times mass is equal to the normal force plus gravity. Now, if our normal force is a positive number like we have here, we are experiencing a push downwards, all right? And that push is to prevent us from going upwards. So if the car is going really fast, the moment we get to the top of the loop, the surface right here is pushing down to prevent the cart from going up. Now, if our normal force is actually negative, then it's actually trying to prevent us from going downwards if we basically switched it. And so the normal force would be pointing this way. Now, however, we don't have a surface over here to keep us going upwards. So what ends up happening is that if our normal force is negative, the cart is going to fall down in free fall. So I'm saying that if our normal force is actually equal to 0, then we've reached the minimum amount of velocity that is required to keep the cart going. So if we just cancel this out because it's 0, we will get that our mass times our centripetal acceleration, which I'll write just v squared over r, is equal to our weight, which is mass times gravity. Now, cancel out the mass, divide it on both sides, multiply the r on this side, and take the square root. You will get v is equal to the positive square root, obviously, because we have a positive velocity, of radius times gravity. So if we just plug that in, we get the square root of 5 times 9.8, and we get 7 meters per second. So that's the minimum required velocity to keep us going. Now notice one thing, the minimum required velocity actually is independent of the mass. all it takes is changing the radius of the circle, and the gravity is also always the same. So the radius of the circle is directly correlated to the minimum required velocity. Nothing has to do with the mass. So that's an interesting note. So you can actually just skip right to this equation. If you remember it, you can use that to basically figure out the minimum required velocity given a situation exactly like this.